In this section, we're going to be talking about indefinite integrals and the net change theorem, as well as getting some additional practice with computing definite integrals. So first we want to talk about the difference between a definite integral and an indefinite integral. So far we mostly have been dealing with definite integrals. So when we write down an integral from a to b of f of x dx, where we have these limits of integration on our integral, this is an example of a definite integral, and this quantity is always a number. So when we compute that value, we're finding our antiderivative, evaluating it at our endpoints, and getting the antiderivative at b minus the antiderivative at a, which is equal to some numerical value. When we talk about an indefinite integral is the most general antiderivative. So we notate this as the integral of f of x dx, and this would be capital F of x, our antiderivative, plus c. So our indefinite integral is a family of functions. Okay, but we can always check our indefinite integral by taking the derivative of the right-hand side and making sure that we get back f of x. So just as a short example of comparing indefinite and definite integrals, if we have the integral from 0 to 1 of x squared dx, we know this would be x squared over 3 evaluated from 0 to 1, which would give us 1/3. So that would be our definite integral where we're getting a numerical value. If we computed the integral of x cubed dx without any limits here, this would be x cubed over 3 plus c. So it would be our most general antiderivative. And if I wanted to check that indefinite integral, I could take the derivative of x cubed over 3 plus c, and I would find this is 3x squared over 3, or x squared, which agrees with what I have here. Okay, so let's take another look at an example like that. So using the techniques that I have so far, I wouldn't have been able to come up with this formula, but I can check this formula by taking the derivative of the right-hand side and making sure that I get back cosine cubed x. And this is good practice for us because we're going to have to recall some of our trig identities to help us verify that relationship. So here I have a formula for the indefinite integral. This is telling me that the indefinite integral of cosine cubed x dx is sine x minus 1/3 sine cubed x plus c. So if I take the derivative of sine x minus 1/3 sine cubed x plus c, I should get back cosine cubed x. So our derivative of sine x is cosine x. The derivative of 1/3 sine cubed x would be 1/3. Let's see, sine cubed x is sine of x cubed, so this would be times 3 sine squared x times cosine x using the chain rule, and the derivative of c would be 0. So I've got cosine x here, let's see, minus sine squared x cosine x. Okay, so we can factor out a cosine x. So we have cosine x, 1 minus sine squared x. And we notice that this has a relationship to cosine squared. Remember that cosine squared x plus sine squared x is equal to 1. So 1 minus sine squared x is equal to cosine squared x. So we can replace this with cosine squared x, which gives us cosine cubed x. Okay, so we were able to verify that that formula is indeed correct. Okay, so let's look at a couple more examples. So here we're interested in finding the general indefinite integral for both of these cases. So in the first one, I have the integral of u plus 4 times the quantity 2u plus 1. And I know that I should do some algebra first to expand that out, and then I can use antiderivative rules of each of the different terms. So I'm looking at 2u squared. Let's see, I'm going to get a 8u and another u here, so this will be plus 9u plus 4 du. And then I can antidifferentiate each one of these terms. So I'm going to have 2u cubed over 3 plus 9u squared over 2 plus 4u plus c. And that would be our answer for the general indefinite integral for that first problem. For the second one here, I'm going to have to use some trig identities to simplify this, because this isn't automatically something that I can use an antiderivative rule on. So remember, we had this identity. I think this has come up once or twice before. Sine of 2x is equal to 2 cosine x sine x, or 2 sine x cosine x. So I can replace sine 2x with 2 sine x cosine x all over sine x dx. And then that allows this to simplify to 2 cosine x dx. And now I can take the antiderivative of that. I have 2 sine x plus c. Okay, so whenever we're doing this general indefinite integral, this is just giving us notation to a problem that we might have had in section 4.9 when we first learned antiderivatives. Now we can say that this integral notation allows me to find that most general antiderivative, so I have that plus c as part of it. So I just want to point out all the different antiderivative rules that we currently have. So we've learned properties for working with our integrals, how we can pull out a constant, or when we switch the order of the limits of integration, that means we're multiplying by a -1, or if we're looking at an integral of a sum or a difference, that's the same as looking at a sum or a difference of the integrals. We also have our power rule, our rule for the integral of 1 over x, the integral of e to the x. We also have a rule for the integral of a to the x. For example, the integral of 2 to the x would be 2 to the x over the natural log of 2 plus c. And we also have our different trig antiderivative rules. This sheet here comes from the Math 108 website that summarizes the various antiderivative rules. So some of these here we haven't learned yet. Just note that 7 and 8 here we will talk about in section 5.5, and 9 and 10 are something that you would learn in Calc 2. But all of these other ones you would be expected to know at this point. We've got all these other trig antiderivative rules, and we've got our inverse trig antiderivative rules, as well as these hyperbolic trig function rules. Okay, so this is a pretty comprehensive list of all the rules that you should know at this point. Okay, so let's go and look at a few more examples. Okay, so let's look at a couple of definite integrals now, just getting practice with our antiderivative rules together with our limits of integration. So what I have here is the integral from 1 to 2 of x over 2 minus 2 over x. So let's see, I've got 1/2, and then I need to multiply that times my antiderivative of x, so that's x squared over 2, minus 2, this is 2 times 1 over x, so the antiderivative of 1 over x is the natural log of the absolute value of x. And I need to be evaluating this from 1 to 2. Okay. So let's see, this is going to be x squared over 4 minus 2 ln absolute value of x from 1 to 2. So I need to plug in that upper limit of 2 first. So I've got 2 squared over 4 minus 2 ln 2 minus 1 squared over 4 minus 2 natural log of 1. Okay, so we've got, let's see, 2 squared over 4, 4 over 4, that's going to be 1. Minus, now I can leave that as 2 ln 2, or I could choose to write that as the natural log of 4 by writing it as ln of 2 squared. Let's see, minus 1/4, and I know the natural log of 1 is 0. So this gives me 3/4 minus the natural log of 4 is the value of that definite integral. Okay. So let's look at a couple more examples, just getting practice with all of these different antiderivative rules that we need to know. So here I'm looking at evaluating the integral from 0 to 1 of x to the 10th plus 10 to the x dx. Okay, so this is making use of that antiderivative rule for the integral of a to the x dx. So note that this rule is a to the x over the natural log of a plus c. Okay. So when we're doing our definite integral here, I'm going to have my antiderivative of x to the 10 first, so that's x to the 11 over 11, plus my antiderivative of 10 to the x, so that's 10 to the x over the natural log of 10. And I'm evaluating this from 0 to 1. So I plug in 1 first, so I have 1 over 11 plus 10 to the 1 over the natural log of 10 minus 0 plus 10 to the 0 over the natural log of 10. So that's going to become minus 10 to the 0 over the natural log of 10, and we know 10 to the 0 is 1, so this is minus 1 over ln 10. So we have 1, oops, my 1 over 11 became 1 over 10, so this should be 1 over 11. 1 over 11 minus 9 over the natural log of 10 is our final answer. Okay, so we want to remember both our power rules here and our rules for things like 10 to the x, 2 to the x, 3 to the x, as well as our antiderivative rule for e to the x. Remember, e to the x would just be a special case of this because it would be e to the x over the natural log of e, which would be e to the x. Okay, so what else can we look at here? Okay, so here's another one where we're needing to use some trig identities to help us compute the integral. So it's important for us to remember all these trig identities. That's why we want to do a couple of these examples for practice. So looking at this, I'm going to want to do a little bit of factoring first. So I've got the integral from 0 to pi thirds of sine theta plus sine theta tangent squared theta all over secant squared theta d theta. So this looks kind of like a mess. So I want to try to simplify it. So I'm going to start by factoring out a sine theta because that appears in both of these terms. So I've got sine theta times 1 plus tangent squared theta all over secant squared theta d theta. And then I should recognize that 1 plus tangent squared theta is associated with a certain trig identity. So remember, we had sine squared theta plus cosine squared theta was equal to 1. And if I divide every term here by cosine squared theta, then I can get the identity that relates tangent and secant. So sine squared theta over cosine squared theta is tangent squared theta. So I have that plus 1. 1 over cosine squared theta is secant squared theta. So I see that I have the identity tangent squared theta plus 1 is secant squared theta. So I can replace this 1 plus tangent squared with secant squared. So I have this integral from 0 to pi thirds sine theta secant squared theta all over secant squared theta d theta. So these nicely cancel for us. So we're just left with looking at the integral of sine theta. So we've got this integral 0 to pi thirds of sine theta d theta. And I know the antiderivative of sine theta is negative cosine theta, since the derivative of cosine is negative sine. So I'm evaluating this from 0 to pi thirds. So I plug in that upper limit first, so I have negative cosine of pi thirds. Now remember, when we're doing our upper limit minus the antiderivative evaluated at the lower limit, I'm going to have minus, and then that minus is also going to appear there. So this is the minus sign for the difference, but then my antiderivative is negative cosine. So I've got minus negative cosine of 0. So that's going to become plus a positive. So cosine of pi thirds is a half. So we're going to end up with negative a half plus cosine of 0, which is 1. So our value for this integral ends up being 1/2. Okay. So the more practice you can get with all of these antiderivative rules, working with both definite and indefinite integrals, the more prepared you'll be when we get to a test, and the more prepared you'll be going into Calculus 2. One other topic that we want to just introduce for a few minutes, and we'll spend more time on in class, is what's called the net change theorem. So this is an application of the second part of the fundamental theorem. Okay, so remember that the second part of the fundamental theorem says that the integral of some function is equal to the difference between the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So in an application, if what you have here that you're integrating is some particular rate, then the integral of that rate is the net change in the quantity. So we'll often talk about this in the context of our rate being velocity. So we'll be looking at the integral from a to b of v of t dt, or in other words, the integral from a to b of s prime of t dt. So our rate will be a rate of change of position with respect to time. And then if I wanted to integrate that rate, I'd be looking at S of B minus S of A, or our total displacement over the interval. If, on the other hand, I wanted to be considering the distance traveled, I'd have to look at the integral from a to b of the absolute value of v of t. Because what the integral from a to b of v of t is taking into consideration is where velocity is positive and negative. So if velocity is positive and then becomes negative and then becomes positive again, and this is my y equals v of t, and I'm going from a to b here, then this integral is going to represent that net area, or that net change in position. So it's going to take into account going forwards and backwards, but just look at my total displacement. If I actually want my total distance traveled, for instance, when we think about displacement, if I started here, I moved here, and then I moved back here, the displacement would only count from here to here, but distance traveled will count this piece plus this piece. Okay, so if I want that total distance traveled, I need to be looking at the integral of the absolute value of my rate function. So this would represent my total distance. So that's an important thing to consider when we're looking at velocity problems. But in general, we're often just interested in a net change. So a standard other kind of maybe net change problem would be a situation where maybe you have v of t represents a volume of water. We've seen a couple of questions that have dealt with a tank that was filling with water. If you knew the rate at which your tank was filling, then you could talk about the amount of the net change in the amount of water between two time periods by looking at the integral of v prime of t dt. So this would be v of b minus b of a. So this would be the net change in the amount of water. Between those two different time periods. Okay, so we're going to do some more examples in class of more kinds of contexts where this net change theorem would come into play. In our example, in the video lecture, we're just going to talk about comparing displacement versus distance traveled. So in this example, I have a velocity function that's given to me as 2t minus 1, so it's a simple function here, over the time interval from 0 to 2. This is for a particle moving along a line, and the velocity is in meters per second. And we want to find both the displacement of the particle over this interval and the distance traveled. So the displacement is just going to be my integral over this interval of my velocity function. So this will just be the integral from 0 to 2 of 2t minus 1 dt. So just using what I know about computing my integral, this is just t squared over 2 minus t evaluated from 0 to 2. So I'm going to have 2 squared minus 2 minus 0. So I get 2 meters is my total displacement. Okay. But what if I want my distance traveled? So if I want my distance traveled, I'm looking at the integral from 0 to 2 of the absolute value of 2t minus 1 dt. And so now I have to consider where my velocity is negative and where it's positive. So remember that our absolute value function is equal to 2t minus 1 if 2t minus 1 is positive, and negative 2t minus 1 if 2t minus 1 is less than 0. So if we look at where 2t minus 1 would be equal to 0, it's at t equals a half. And if I were to make a little sign chart here for 2t minus 1, I know that if I plug in something smaller than a half, I have something that's negative, and something bigger than a half, I have something that's positive. So this indicates that I should break up this integral from 0 to 2 into an integral from 0 to a half and from 1/2 to 2. So this is going to be from 0 to 1/2 of the absolute value of 2t minus 1 plus the integral from 1/2 to 2 of the absolute value of 2t minus 1 dt. Okay, and now I can use my definition of absolute value here to replace each of these pieces. So I'm going to have the integral from 0 to 1/2. Now the absolute value of 2t minus 1 should equal negative the quantity 2t minus 1 on that interval. in order to make that a positive quantity, since 2t minus 1 is negative on the interval from 0 to a half. And then this is going to be plus the integral from 1/2 to 2 of 2t minus 1, where I can drop those absolute value bars since 2t minus 1 is positive when t is bigger than 1/2. So here I would just be taking my antiderivative of each of these two pieces, and to save us a little time, I'll skip some of these steps here and show that we would get this is equal to 5/2 meters. So our total distance traveled is 2.5 meters, whereas our displacement is 2 meters. Okay, so we'll talk more about this topic in class, and please let me know if you have any questions.